All right, welcome back. Chapter 3. But before we go into chapter 3, I think there's something I forgot in chapter 2 which I have to draw your attention to. Take note, a typical example can be asked, why does sulfur exhibit +2, +4, +6 oxidation numbers? Whereas oxygen only has one oxidation number of +2. Why? Now, the gospel truth about it is that oxygen belongs to the L shell. And of course, the L shell has an energy level of 2, while the value of L is going to be 0 and 1. 0 is to s orbital, 1 is to p orbital. So that means oxygen only has 2 degenerate orbitals. Or let me just say two same level orbitals, which are 2p and 2s. But if you're talking about degenerate orbitals, you have 1 for s and then 3 for p, which is 4 degenerate, okay? So, but as for sulfur belongs to the M shell. And the M shell is on the third energy level. And that is to say the value of L is going to be 0, 1, and 2. 0 for s, 1 for p, and then 2 for d. So, sulfur has a vacant d orbital, which it can use to give it multiple oxidation numbers. For example, when sulfur decides to use one electron from its p orbital, because if you write the configuration, you will discover that the p orbital of sulfur has 4 electrons. The first orbital is double, while the other 2 out of the 3 is single. So it can use that one electron from its px orbital and spin it into the first bulk in the 3d orbital. And by so doing, you have 4 unpaired electrons, 3 from the p and 1 from the d. And that makes it have an oxidation state of 4+. Now, it may also decide not to even, eject one of its electrons and make use of the 2 unpaired electrons in its p orbital. So that just leaves it at 2+. Now, for the 6+, that one can come when it decides to eject the only one double electron on the p orbital and one from its s orbital into the d orbitals, and you discover that you have a total of 6 unpaired electrons. So this is the basic reason why sulfur can have up to 3 different oxidation numbers, while oxygen has only 1 oxidation number. The gospel difference is they are not of the same shell, right? So that takes us to hybridization proper. Now, what is hybridization? Hybridization simply means mixture or combination of 2 or more things to form one. If I decide to mix 2 things to form another, it has been hybridized, okay? Good. So, for example, if I mix salt and water to give me a solution, that's a hybrid solution of salt and water, right? Same thing with sugar and water, as the case may be. So, if I decide to take an s orbital and mix it with a p orbital to have an sp hybridization, that's a hybrid, hybridization. So, hybridization in chemical term now is simply the mixture of atomic orbitals of the same or nearly the same energy level to form new hybrid orbitals. The mixture of orbitals of the same or nearly the same energy level so as to form new hybrid orbitals, you refer to that as hybridization. Now, for hybridization to occur, there are some conditions that one must take note of. Number 1, the orbitals must be of the same or almost the same energy level. That's 1. Then number 2, hybridization of orbitals usually takes place from the atom's valence electron. So hybridization always takes place from the valence electron of the atom, okay? Then number 3, hybridization of orbitals can take place between totally filled, half-filled, or even empty hybrid orbitals. Very important. So it must not be partially filled orbitals that participate in hybridization. Totally filled orbitals participate in hybridization. Typical examples to that is oxygen, nitrogen. There you see 2 filled s orbitals or 2 filled electrons in the s orbital completely filled, participating in hybridization to give you sp3. Important notice as far as hybridization is concerned, or what are the importance of hybridization? Number 1, it reveals the molecular shape or the molecular geometry of the molecules. And then number 2, it shows how bonding occurs among atoms. So these are the advantages of hybridization. It reveals the geometry of the molecule and then also show how bonding of atoms or bonding of atomic orbitals, how it takes place. That is what it does. Facts about hybridization. Number one, remember, during this fact, I can repeat what I have said in the conditions for hybridization to take place, okay? So facts are facts. Number one, the number of hybrid orbitals formed is equal to the number of atomic orbitals mixed. That's the gospel truth. So if you have sp3, that simply means you have 4 hybrid orbitals. So the number of hybrid orbitals formed is equal to the number of atomic orbitals mixed. That's one. Number two, hybridization must not take place in all half-filled orbitals. Part can participate while the other part does not participate. So that invariably means that if you have 3 unpaired electrons in the p block or p orbital, for example, all the 3 of them must not participate in hybridization. Yes, only 2 can decide to participate in hybridization while the remaining 2 remain unhybridized. And whenever they remain unhybridized, they usually lead to what we call pi bond formation. Next, completely filled orbitals can also participate in hybridization. Of course, we have discussed that, and we gave you examples of oxygen, nitrogen, as the case may be. Hybridization can only take place during bond formation and never in an isolated gaseous atom. Never. An isolated gaseous atom cannot participate in hybridization. Why? It only takes place during bond formation. If you are isolated, you're on your own, you can't hybridize with yourself. It makes no sense. All right. Next, the shape of the molecules are always predicted from the number and types of hybrid orbitals. Oh yes. The shape of the molecules are always predicted from the number and type of orbitals. What do we mean? If you give the shape of a particular orbital to be linear, or a particular molecule to be linear, it simply means that you have drawn that name linear from the number and type of hybrid orbitals. For example, you have sp for linear. That means you have s orbital and p orbital. If you have trigonal planar, you're talking about sp3 or sp3, that's the case may be. If you have tetrahedral shape, you're talking about 4 orbitals, and the 4 orbitals you're talking about are 1s and 3p orbitals. Okay, so what we are saying is that the shape of the molecules are always predicted by the number and type of hybrid orbitals. Okay, so if you have 7 hybrid orbitals, then you're talking about 1s, 3p, and how many? And 3d. Yeah, 3d, to give you 7 hybrid orbitals, and the name of that becomes pentagonal bipyramidal, if I'm not mistaken. And the typical example of that, an element that can form such compound, is iodine. Iodine, because it has 7 unpaired electrons in its outermost shell, and those 7 unpaired electrons can participate in hybridization. All right, so let's take us to the next stage. The bigger lobe of a hybrid orbital always have the positive sign, while the smaller lobe of a hybrid orbital always have the negative sign. This is just sign definition on hybrid orbitals, okay? So nothing much about it. Take note, the reason why there is a bigger lobe and a smaller lobe is because the electron density in a lobe determines the size of the lobe. If the lobe is big, it has more electrons embedded in it than in the other side. So the electron density we are talking about is the quantity of electrons per unit size of the orbital. Okay, but let me not go into those details because you don't need them. Next, what is an orbital? An orbital is simply a space around the nucleus where there are high probability or high chances of finding an electron. A region or space around the nucleus where there is high probability of finding an electron is called an orbital. And of course, electrons are usually found either on the x, y, or z axis around the nucleus. There are basically 4 types of orbitals: the s orbital, the p orbital, the d orbital, and the f orbital. The s orbital is spherical in shape. It has a maximum of 2 electrons inside one subshell, and it is spherical, as I said. The p orbital is dumbbell in shape. It has 3 subshell orbitals, each of them with 2 electrons, making it a total of 6 maximum electrons it can carry. The first subshell is the pz, second is py, third is pz. And of course, it's dumbbell. Each electron can be within each side of the dumbbell. And of course, the bond angle, or not really bond angle now, the px orbital actually has its dumbbell-shaped line on the x-axis, while the py suborbital, when electrons are there, they are lying on the y-axis, while the pz, when electrons are there, they are lying on the in between the x and the y-axis. Okay, that we call the z-axis. And of course, the pz, the px, and the py, all of them are 90 degrees to each other. Very important. The d orbital is double dumbbell. It has a total of 5 subshells, and each of these subshells has 2 maximum electrons they can carry, making it a total of 10 electrons in the d orbital. And of course, the first part of the d orbital is the dxy, followed by the dz, the dxz, followed by the dyz, right? So the dxy simply means electrons revolving between the x and the y axis. The dxz, electrons are revolving between the x and the z axis. The dyz, electrons revolve between the y and the z axis. Now, the last two are the little bit more crucial ones. The dx squared minus y squared and the dz squared. Now, the dx squared minus y squared orbital, or suborbital as the case may be, means that electrons revolve either in the x or in the y axis. It doesn't revolve in both now. It's either in the x or the y axis. Then the last one, which is the dz square, simply signifies that electrons revolve on the z axis. You get it? If you don't get it, forget about it. So that takes us to hybridization of carbon. Hybridization of carbon. Carbon undergoes only 3 types of hybridization, which are the sp, sp2, sp3 hybridization. Now, the reason why carbon can only undergo 3 types of hybridization is because of the number of electrons it has in its outermost shell, which is 4 valence electrons. If it was able to possess more than 4 valence electrons, then it could go beyond. So, and remember, the number of hybrid orbitals is equivalent to the number of valence electrons. You know, carbon has 4, so the maximum it can go is sp3. That means 1s and 3p, making it 4. Now, if you look at phosphorus, for example, that has 5 electrons in its outermost shell, it can go beyond sp3. And that is why you see sp3d. That d you see is as a result of 1 electron extra compared to carbon. Because carbon is 4, sulfur is 5. Now, if you look at sulfur, sulfur has 6 electrons in its outermost shell. So it can take a step further to have sp3d2. And then if you look at iodine or chlorine, for example, that has 7 electrons in its outermost shell, can take it to a higher level, which is sp3d3. You get it? All right. So that is just a brief summary of what happens. But however, let's go into details. Let's start with the sp3 hybridization. In the sp3 hybridization, 4 hybrid orbitals participate, 1s and 3p, and all of them do that in the ratio of 25% each. And of course, carbon is a practical example. Now, carbon at ground state has 2 electrons in each orbitals, right? And the last orbital, which is the p orbital, has 2 electrons. At excited state, 1 electron will jump from the 2s orbital into the 2p orbital to make it 3. And then they will now blend 1s and 3p to give you sp3, right? So that is how an sp3 hybridization occurs. Now, the hybridization of carbon at excited state, if you want to write a configuration, is 1s2, 2s1, and then 2p3, right? Good. A typical example of elements that can undergo this sp3 hybridization are, number 1, water molecule, yes, ammonia, methane, name them. Now, take note, very important. Methane is a very prominent example of an sp3 hybridization and has a bond angle of 109.5 degrees. That's methane, 109.5 degrees. And it's also important for you to know that water, or let me start with nitrogen because nitrogen is the next. Nitrogen actually can undergo hybridization to form sp3. How? Because when you write a configuration of nitrogen at ground state, the p orbital has 3 unpaired electrons. So an electron will not jump from the 2s2 into any of the 2p's because they are all filled. with one electron. So what will happen is the 2s2 will just amalgamate itself with the p3. So you are going to have 2 electrons in the s orbital and one electron in the p orbital. And when that happens, each of these subshells will now become sp3, sp3, sp3 each. However, the double electron you found in the s orbital accounts for what we call a lone pair of electrons. This lone pair of electrons have a way of pushing down the legs of the ammonia to reduce the bond angle between the hydrogen atoms. So the bond angle is going to reduce from 109.5 to 107.3 in ammonia. In water, the same thing happens. Water will have 2 unpaired electrons and 2 lone pairs. So the bond angle is going to reduce from 107.3 to 104.5. That is water molecule, and that's a bent shape, right? So that takes us to sp2 hybridization. Of course, this type of hybridization takes place between 1 s orbital and 2 p orbital. Each of them participate with 33%, 0.33 as the case may be. And of course, carbon is still the typical example. In a type like this, an electron will always jump from the s orbital into the p orbital to make it 111. But what happens is that only 2 electrons will participate in the hybridization process, leaving one unpaired, one unhybridized electron. Now, the one unhybridized electron that will remain will form what we call a pi bond in the future. So that is the essence of the one that does not hybridize. It forms a pi bond. And then, of course, the bond angle in such an sp2 hybridization is 120 degrees. And therefore, it is given a shape of trigonal planar. No longer tetrahedral. Tetrahedral is for sp3. Trigonal planar is for sp2. And typical examples of sp2 hybridized elements are ethene, that's ene, ethene, that's C2H4. And then you can also have other examples like HNO2. Yeah, HNO2 is a very common, it's a very confusing one. Hybridization is 2. Why? Because you got to draw the structure very well, bro. First, you have hydrogen, up you have oxygen, down you have nitrogen, up again with 2 bonds you have oxygen. So you discover that the oxygen there has 2 lone pairs, while the nitrogen there has 1 lone pair. So by the time you calculate the hybridization, you discover that it's sp2. And the big question is, how will I be able to predict that it's sp2? Because the shape is bent. The shape is bent. You're going to see that when you draw that yourself. So it's important for you to know that the bond formed between a sigma bond. I want to talk about sigma bond and pi bond formation. I think this is very key as far as this topic is concerned. Sigma bonds are formed from the head-on intersection of orbitals. Yeah, head-on intersection of orbitals. They are usually far stronger than pi bonds. For example, an s orbital head-on with a p orbital gives you a sigma bond. A p orbital head-on with another p orbital. What I mean p orbital is dumbbell shape now. Dumbbell to dumbbell head-on will give you another sigma bond. Or you have a dumbbell with a double dumbbell meeting with one of them at the head will give you a sigma bond. In this time around, this is p orbital with d orbitals, that's pd, right? Then when you have 2 s orbitals, can always give you a sigma bond, right? Now, this arrangement makes a sigma bond stronger than a pi bond because of the enhancement to free rotation of the orbitals without breaking. So that invariably means that when they meet head-on, they can easily rotate without breaking bonds. So that makes a pi bond far stronger, a sigma bond far stronger than a pi bond. It may interest you to hear that a sigma bond has a potential of exactly 347 kilojoules per mole. What does that mean? That simply means that you need a total amount of energy of about 347 kilojoules of energy to break one sigma bond. 347 kilojoules of energy just to break one sigma bond. But as for a pi bond has a capacity of 246 kilojoules worth of energy to break one pi bond. Well done. Same here. Sorry, I had to greet a friend. So hence, a pi bond is weaker than a sigma bond. However, take note, 2 pi bonds are stronger than 1 sigma bond. And remember, a pi bond is a single bond, not a double bond. Pi bonds are only formed in the presence of a sigma bond. And in their formation, they are always formed by side-by-side overlapping of orbitals. 2 dumbbells can side-by-side overlap with each other to form a pi bond. And the reason why they are weak is because when rotation takes place, the bond breaks, So they are pretty weak. Very, very weak. So typical examples of other elements you can see on sp2 hybridization is boron trifluoride, sulfur 6 oxide. You can draw them, you can predict their hybridization, and you just get that right. Very simple and straightforward. Now we go to the next, which is sp hybridization. Of course, here you have 2 orbitals s and p, each of them participating with about 50%, one s and one p. And a typical example here, which you can always use carbon, but here only two electrons will participate in the hybridization, one from the S, one from the P. And when that type of reaction occurs, it forms an sp hybridization. A typical example is C2H2, and that's ethine, YNE, C2H2, right? And the bond angle in them is 180 degrees, and the shape is linear. And of course, it has 2 sigma bonds because it has 2 unhybridized electrons. 2 unhybridized electrons or orbitals, as the case may be. And those 2 unhybridized orbitals or electrons will actually form 2 pi bonds. And then the sigma bond will just be at the middle, right? Very important. Take note, barium chloride is a typical example of sp hybridization, even beryllium hydride. And the reason is because beryllium has a vacant p orbital. Oh yes, it belongs to the L shell, so it has a vacant p orbital, which it can use only during hybridization. And that takes us to the next, which is sp3d hybridization. sp3d hybridization makes up of 5 hybrid orbitals, 1s, 3p, and 1d, each of them contributing 20% to the hybridization process. Taking phosphorus as a typical example, because phosphorus has 5 unpaired electrons in the outermost shell. Remember, phosphorus belongs to the M shell, having a d vacant orbital. Yeah, because the energy level is 3. The first energy level 1. The second is 8. So phosphorus is in the third energy level, right, where you have 18 electrons. So at that point, you have L to be 0, 1, and 2. 0 for s orbital, 2, 1 for p orbital, d is for the other one. So 3, 3, 3. 3s, 3p, 3d. So it has a vacant 3d orbital, which it can use during the hybridization process. And of course, 1 electron will have to jump from the 3s2 into the 3d orbital. At the end of the day, each of them will hybridize to form sp3d, each 5 hybrid orbitals. And of course, you can write a configuration of phosphorus both at ground state and at excited state. Now, the bond angle is quite an amazing one. Because there are 5 hybrid orbitals, first, it forms a trigonal shape sideways. That means it has 3 orbitals sideways, like that of a fan, each of them at 120 degrees. And then it has 2 vertical ones, vertically upward, that is at 180 degrees to each other. So on that note, because of the 3-sided sideways shape, that makes it trigonal. Then the up and down makes it bipyramidal, because you have 3-sided shape up and 3-sided shape down. So that makes it trigonal bipyramidal. And the bond angle is 90 degrees and 120 degrees. Now, the 90 degrees we're talking about is the bond angle between the top and the sideways, and then the side ones are at exactly 180 degrees. So 90 and 180 is trigonal bipyramidal. That takes us to, and a typical example there is phosphorus pentachloride. You can draw that, it's very simple. So that takes us to the sp3d2. Of course, there you have 1 sulfur, 1 s orbital participating with 3p orbitals and 2d orbitals, each of them contributing to 16.67, right? Good. Now, taking sulfur as a typical example, having 6 electrons in the outermost shell, of course, also having a d vacant orbital, will definitely have to promote an electron, 1 from its p orbital and 1 from its s orbital into the d orbitals. And at the end of the day, you will have a total of 6 hybridized electrons, each of them being sp3d2 hybridization. And of course, if you look at the shape is going to have 4 electrons or 4 orbitals on the side, no longer 3, 4. So because there are four shapes, 4 orbitals on the side, making a square shape, that makes it octahedra. That makes it octahedra. Now, one would have said, why octahedra when you have 4 up and 4 down? Why not call it tetrahedral bipyramidal? Instead of saying tetrahedral bipyramidal, you just call it octahedral. And of course, the bond angle between each of them is 90 degrees. And a typical example of that is sulfur hexafluoride. Sulfur hexafluoride will do that for you. And then take note, sulfur tetrafluoride is seesaw in shape, not trigonal bipyramidal, due to the presence of 1 lone pair of electrons. Yes, the lone pair of electrons there prevents it from being trigonal bipyramidal. Now take note. You have to be very careful with that, and you should be able to understand the job of lone pair towards shape determination. We are going to see that as well. So that takes us to the last part, which is the sp3d3 hybridization. And of course, it's made up of 1s, 3p, and 3d, each of them participating with 14.3% of the hybridization process. Now, taking iodine as a typical example, iodine has the configuration of krypton 36, 5s2, 4d10, and 5p5. Now, the 4d10 will not participate because it has a lower energy level than 5s and 5p. And remember, iodine also has a vacant 5d orbital. So it will only participate between its 5s, 5p, and 5d orbital. As for the 410, it will not participate because the energy level is lower. Remember, the law says that hybridization takes place between same energy level or nearly the same energy level. 4 and 5 is quite far. So when you conduct the hybridization process, you discover that 1 electron will jump from the 5s orbital to the d, and then 2 electrons will jump from the 5p orbitals to the d. At the end of the day, you will have 7 hybridized orbitals, each of them being sp3d3 each. And of course, the nomenclature of this type of element is pentagonal bipyramidal. And a typical example is iodine heptafluoride. On the sides, you have a total of 5 shapes. That's 5 orbitals on the side, then 1 up and 1 down. So pentagonal on the side, then the top and the down, which is 180 degrees to each other, will now bring about the bipyramidal. So you have 5 shape up, 5 shape down, pentagonal bipyramidal. And the bond angle is 90 degrees and 72 degrees, respectively. So that takes us to the shapes and molecules. Very important. Shapes and molecules. This is an aspect that you shouldn't forget. Shapes and molecules are key, and they are very, very important. So I'm going to read them and try as much as I can to make you fathom how the shapes looks like. Number 1 is linear. Linear, of course, from the word linear, sideways, okay? Straight. You have a black spot in between and then 2 on black spots by the side. 180 degrees as bond angle. Then the trigonal planar. Trigonal planar is just 1 up and 2 legs down, okay? 1 up and 2 legs down. That's trigonal planar. And the bond angle is usually 120 degrees. Then the next one is tetrahedral. Tetrahedral is not 4-sided figure like that, the way it should be at 90 degrees on a plain paper. No, you just have 1 projected upward and 3 legs like a tripod stand, okay? That is a tetrahedral shape. And that is why the bond angle is not 90 degrees, but 109.5. Do you get it? All right. So that takes us to the next one there, which is the bent shape or the V shape. Just like the name implies, V shape is V in nature. It has a lone pair. The presence of a lone pair makes it V shape or bent shape, as the case may be. If it is water, 2 lone pairs. If it is nitrogen, 1 lone pair. Next, trigonal pyramidal. For example, ammonia, trigonal pyramidal. For trigonal pyramidal, you have a lone pair and 3 legs. So it is just like the trigonal planar. Sorry, I said trigonal planar. It's just like tetrahedral shape. Instead of that 1 knob at the top and 3 legs, so remove the knob at the top and put what we call lone pairs. That gives you trigonal pyramidal. And then the next one here is the trigonal bipyramidal. Trigonal bipyramidal is just almost the same thing with trigonal planar. It has one leg up and four legs down. One leg up and four legs down. And that gives you trigonal pyramidal. And you can do that, or another way you can remember it is three-sided figure. That's on the sideways, three orbitals at 120 degrees to each other, and then one up and one down at 180 degrees. So three shape up, three shape down, trigonal bipyramidal. Then the next one is seesaw shape or sawhorse shape. Very funny name, sawhorse shape. And this one is just like four orbitals on the sideways with one lone pair, in between the two at the top. That's seesaw. And a typical example of that is sulfur tetrafluoride. And then we go to the T shape. Now the T shape is just like the cross, okay? Just like the cross of Christ. Just remove the head and put two lone pairs. That will give you the T shape. And that takes us to the next one, which is linear shape. Yeah, we've discussed linear before, but it's an advanced linear shape again that comes with three lone pairs. It is sideways and has two lone pairs up and one lone pair down, linear. And then next one is octahedral shape, that is made up of four orbitals on the side. Of course, each of them may be at a bond angle of 90 degrees to make it 360, and then one up and one down. So you have four up and four down. So that is octahedral and not tetrahedral bipyramidal. All right. So the next one there is the square pyramidal shape. Square pyramidal is just like the one-sided octahedral. So you have four orbitals on the side and one down, but you don't have it repeated itself on the top. So that gives you the square pyramidal shape. So what you have at the top, instead of one knob, is just a lone pair. So you have four-sided orbitals with one lone pair at the top and then one knob at the bottom. Then the last shape we are going to discuss is the square planar. And the square planar is just like four-sided orbitals with one lone pair up and one lone pair down. Square planar. So basically that is that for the shapes of molecules. So we are going to go into a table that will help you remember very well the concept of hybridization. So to draw this table, you have the following subheadings. Number one, the number of hybrid orbitals. Number two, hybridization. Is it sp, sp2, sp3? Then the next one is the geometry, okay? The geometry. Is it tetrahedral, trigonal, bipyramidal, stuff like that. Then the next one is the bond pair. After the bond pair, you have the lone pair. After the lone pair, lastly, you have the molecular shape, right? You have the molecular shape. The shape and the geometry are not the same. What brings about difference in them is usually the presence of lone pairs, okay? Usually the presence of lone pairs. For example, a four hybrid orbital will have a shape, a geometry of tetrahedral, but the fact there is when lone pair comes into play, one lone pair, you now have a trigonal bipyramidal, two lone pairs bend shape, three lone pairs linear. You see? So what brings about the variation actually is the presence of lone pairs. So let's start with the first one there. The number of orbitals being 2, of course, the shape, the hybridization is sp. The shape is, of course, linear. If there is only 2 bond pairs and 0 lone pair, of course, that's linear. Now we go to the next. Number of hybrid orbitals, if there are 3, that means it is sp2, and that's trigonal. Now, if there is no lone pair at all, that means you only have the 3 bond pairs, that's trigonal planar. If there is 1 lone pair and 2 bond pairs, that makes it a bent shape, right? Just like water molecule. All right. So the next one is number of hybrid orbitals, which is 4. That's sp3. Of course, that's tetrahedral. If there is no lone pair at all, it's tetrahedral. If there is 1 lone pair and 3 bond pairs, that's trigonal bipyramidal. Yeah, trigonal bipyramidal. Sorry, trigonal pyramidal, not bipyramidal. Trigonal pyramidal, that's ammonia. If there are 2 lone pairs and 2 bond pairs, that's bent shape. If there are 3 lone pairs and 1 bond pair, that's how many? That's linear. For example, HCl. Next, 5 hybrid orbitals, and that is sp3d. And the name or the geometry is trigonal bipyramidal. If there is no lone pair at all, that gives you a trigonal bipyramidal shape, just as it is in the geometry. If there is one lone pair and 4 electrons, that becomes seesaw or sawhorse, as the case may be. And I gave you a typical example of that, which is sulfur tetrafluoride. If there are 2 lone pairs and 3 bond pairs, that becomes a T-shape. Do you remember? We discussed that. And a typical example of a T-shape is chlorine trifluoride. And then if there are 3 lone pairs and 2 bond pairs, that becomes linear. Of course, the Oga of linear, 3 lone pairs, 2 at the top, 1 at the bottom. And a typical example of that is xenon difluoride. So that takes us to 6 hybrid orbitals. At 6 hybrid orbitals, you have sp3d2, and the name is octahedral. If there is no lone pair at all, that means there are 6 bond pairs. That means it is octahedral in shape, and that is S. A typical example is sulfur hexafluoride. If there is 1 lone pair and 5 bond pair, that becomes a square pyramidal. Square pyramidal. That means the lone pair is at the top, while you have 4 legs, 4 sides, and 1 leg down. And a typical example of that is boron pentafluoride. Then if there are 2 lone pairs and 4 paired electrons, that becomes a square planar. And a typical example of that is xenon tetrafluoride. And that takes us to 7 hybrid orbitals. And the 7 hybrid orbitals, you have sp3d3. And the name is pentagonal bipyramidal. And of course, if there is no lone pair at all, it's pentagonal bipyramidal iodine heptafluoride is the example. If, however, you have 1 lone pair and 6 bond pair, it becomes pentagonal pyramidal. Another name for that is distorted octahedral, and the typical example is xenon hexafluoride with bond angle of 72 degrees and 90 degrees, just like you find in, what is the name of that buncombe element again? Just like you find. All right, so back to that, I had a short course. So 72 degrees and 90 degrees, just like you find in, what is the name of that element again? I think I saw that not quite long. All right, good. And that is simply octahedral shape, okay? I think, no, octahedral shape is 90 degrees all through. Come on, how come I forgot that? We have 90 degrees and 120 degrees. Okay. Well, I have to let that go so that it won't chop much of my time, okay? Oh, now I have seen that. That is pyramidal. That is actually pentagonal bipyramidal. That's exactly what we're talking about. All right, so the next thing we're going to look at is a calculation part, okay? Now, how do you apply a shortcut to calculating the hybridization of a particular compound? For example, if you're given methane or xenon oxo pentafluoride, how do you calculate that? Simple. The first thing is number of hybrid orbitals is equal to the number of lone pairs plus the number of surrounding atoms. This works for everything except one guy called sulfur. It's called trioxo sulfate 4. That's the only element that doesn't obey this law. So number of hybrid orbitals equals number of lone pair plus number of surrounding atoms. So let's start with an example like methane. Methane has a number of lone pair of 0 because it has 4 electrons. Hydrogen will occupy all the 4 of them. You have to apply Lewis structure, okay? You have to be smart enough to know how to apply Lewis structure for this law to work for you. Carbon, which is the central atom, has 4 surrounding atoms of hydrogen. So there is 0 lone pair and the total surrounding atom is 4. So that means the number of hybrid orbitals is 4, and that's tetrahedral in shape, and the angle is actually 109.5, right? So carbon 4 oxide, for example, has 0 lone pair but 2 surrounding atoms, and it's linear in shape, and that's 180. Ammonia has 1 lone pair because the nitrogen there is the central atom surrounded by 3 atoms with 1 lone pair. So that's trigonal pyramidal. You see that there because of the presence of 1 lone pair. Xenon tetrafluoride, for example, has 2 lone pairs. Now the big question is, how do you get the number of lone pairs to be 2? Xenon has 8 electrons in the outermost shell. So you apply Lewis structure. Fluorine will destabilize up to 2 or 4 of those electrons. At the end of the day, it will have 2. Even the ones that are appearing as lone pair, it will divide them. After dividing them and occupying the 4 different combinations, it will leave behind 2 lone pairs and then 4 surrounding atoms, making it 6, and that is square planar. Then xenon oxo tetrafluoride has a total of 1 lone pair. Yes, 1 lone pair. And how many surrounding atoms? and a total of 5 surrounding atoms. What do we mean? Xenon is actually the central atom there. Oxygen will take 2, fluorine will take 4. So you will just have 1 lone pair remaining, and that is square pyramidal. Triazonitrate 5 ion, that negative sign actually belongs to nitrogen. It means nitrogen has gained 1 electron. So the 1 electron gained by nitrogen will now make nitrogen to have 8 electrons. Each of the oxygen will collect 2 electrons, and at the end of the day, you will have 0 lone pair and 3 surrounding atoms, and that's trigonal planar, sp2. And then you also have NO2+. NO2+ has a lone pair of 0 and a surrounding atom of 2, and that's linear in shape. You can do that of ammonium and all that. So the only disobedient element here is trioxyl sulfate 4. Why? Because trioxyl sulfate 4 actually is AYR. You can verify. There are a lot of questions unanswered about that element. Now, how many sigma bonds and pi bonds are found in the compound below? That's another typical example they can ask you. They will just write a structure, an organic structure, and they ask you how many sigma bonds and pi bonds. As for the sigma bonds are carbon-to-carbon single bond. They are always more than pi bonds, while pi bonds are always attached in double bonds or triple bonds, okay? So just pick the number of pi bonds from there, and sigma bonds, you're good to go. Then, as for hybridization, sp, sp2, sp3, when you are given a structure, just look for the number of surrounding atoms. That will give you the hybridization in one compound, in one atom in a structure. For example, carbon-to-carbon single bond, one carbon has 4 surrounding neighbors, that's sp3. If one carbon has 3 surrounding neighbors, that's sp2. If one carbon has 1 surrounding neighbor or 2 surrounding neighbor, that's sp. You know, stuff like that. So just look for surrounding neighbors and you'll be able to make your hypothesis proper. And of course, when there are lone pairs, take the lone pair as 1 neighbor, okay? For example, you can have nitrogen, then carbon up and down, this one and that, you put lone pairs. If it is oxygen that has 2 lone pairs, take those 2 lone pairs as what? As surrounding neighbors, okay? So you will have to count them properly. And the reason being that at times they will not put those lone pairs for you. For example, COOOH, they will just put double bond O. So you should be able to tell the hybridization from there, right? Then a typical example again will be, there is this school of thought that says that all carbon-to-carbon double bond are sp2. Take note, when you have carbon-to-carbon double bond appearing almost simultaneously, successively, what do I mean? Carbon-to-carbon single bond, the next stage carbon-to-carbon double bond, followed by carbon-to-carbon double bond again, before you have single bond. The second carbon-to-carbon double bond is not sp2, rather sp, because it only has 2 neighbors, right? And then a benzene ring, all carbon atoms in a benzene ring of sp2 hybridized. It is a law, it is a fact, and it is factual. And that is the end of hybridization. Wish you all the best. Thank you for listening, and see you in the next chapter, which is state of matter. An amazing chapter on its own.